We've been working rigid body kinetics problems, and now today we're going to apply the principle of work and energy to those types of problems. That builds on what we've learned in particles. We give the symbol U to the work done by a force, and again, as we did with particles, if the force is a constant one, then the work done between 2 points is just the force times the distance in the same direction of the force. So force times displacement as long as they're in the same direction. For weights, we have a special formula for that, although it really is the same as the one above here. Remember that the work done by a weight only depends on the vertical displacement of the weight. And if you look at the signs here, just remember that if a weight is falling, it's doing positive work. If the weight is being lifted, then it's doing negative work. And we also had this expression for spring that involved the initial and the final deformations of the spring. Now, of course, what could be different for a rigid body is that it could be, we could have an applied moment doing work. And just like the force is the magnitude of the force times the displacement, similar for the moment, except that the displacement, of course, will be the angular displacement. And the units of work and of the moment are the same. For example, foot-pounds or Newton meters, which means that the angular displacement theta must be in radians for the units to work out correctly. Now, we're going to relate that, of course, to kinetic energy of the system. And so when we have a particle, remember the kinetic energy is 1/2 mv squared. But when we have a rigid body, we've got rotation going on at the same time, and there's energy required for that as well. So for the rigid body, we still have the 1/2 mv squared, but we have to be specific that it is the velocity of the center of mass into that part of the expression. And then 1/2 times the mass moment of inertia times the angular velocity squared gives us the total kinetic energy. And our principle says then that we look at the initial kinetic energy, add the summation of all the work done by the particles, will give us the final kinetic energy. Now, one note here that we work a lot of problems where we have a wheel that rolls without slipping, and we know there's a friction force. Now, if we were sliding, we would say that that friction force is doing negative work. But because of the fact that the point of contact where the friction is acting has a velocity of 0, it turns out the friction force that causes that wheel to roll does not do any work, so we don't have to worry about that when we're summing up the work done. In fact, if we look at an example problem like this, we're going to drop this roller or let it go from rest, and we want to know how fast it's going after it's rolled a certain distance down a ramp. And again, the assumption is that it rolls without slipping. So if we start from rest, then the initial kinetic energy is equal to 0. We said the friction doesn't do any work, so the only thing doing work in this case is the weight, and so the weight times the vertical distance that it drops, again positive work, will be the only work that's done here. And our final kinetic energy will be 1/2 mv squared, again v of the center of mass, plus 1/2 I omega squared. And of course, if there's no slipping, then we know that the velocity of the center point is just r times omega. So it's only one unknown there, and we can solve this problem. Here's one we've looked at before. We want to find out what this guy's speed is right before he hits the ground. And we looked at this with our equations of motion, but now we want to use work and energy to do the same thing. And again, we are taking into account the mass of the pulley, so there is going to be energy required to turn the pulley. And so we do start from rest again, so the total kinetic energy is 0 here. Now we have a couple of things doing work, and this time we've got both weights. The weight of the man as he drops is doing positive work. The crate is rising by the same distance, and that's doing negative work. The kinetic energy, there are 3 terms of that. There's 1/2 mv squared for the man. There's 1/2 mv squared of the crate. And finally, because we're not ignoring the mass of the pulley, is 1/2 I omega squared of the pulley. And so when we set T1 plus the work done equal to T2, there's really only one unknown here because the velocity of the man and the velocity of the crate are going to be the same. And if there's no slipping of the rope on the pulley, then we know that either one of those velocities is equal to R times omega. So we can solve for the single unknown, which is just the velocity. And so next time we'll finish up our topic and we'll look at conservation of energy where we have only conservative forces present.